So last time we looked at some simultaneous equations, if you remember, and we came across one that involved quadratics. And so that means there are two solutions. And if we look ahead, or we look back, we have this example, if you remember. We had two simultaneous equations, 1 and 2. And it turns out that because one of them has an x squared in it, that's what makes it a quadratic, and that there are two solutions. And we decided to try and solve these things. We went through it as far as we could. We have to be able to solve quadratic equations. So that's what we were doing last time. So today I want to look at solving quadratic equations. The methods we're going to use assume that the right-hand side is 0 and that the left-hand side has the form ax squared plus bx plus c. So in other words, ax squared plus bx plus c equals 0. Okay, so that means we end up with an equation in this form. Ax squared plus bx plus c equals 0. It has that sort of form. The right-hand side must be 0. So if it's not, we shift everything over to the left to make sure it is 0. And all this is saying is that generally there may be a term involving x squared, in which case there will be a number in front of it. If it's just x squared on its own, that means the number in front of it is 1. So a is 1. There might be a term involving x, in which case there'll be a number in front of that, a coefficient of x, which could be 1 or any value. And there may well be a constant, some number on its own. It could be that there's no term involving x, in which case b is 0. It could be that there's no constant, in which case c is 0. And it could be that a is 0, in which case there's no x squared term and it's not a quadratic equation, so then we'd solve it like we've been doing before. Okay? So you may know that there's a general formula to solve a quadratic equation that we're going to come to, but it's worth pointing out that if b or c are 0, then actually there's a much easier way to solve the quadratic equation. So what I want to do is look at the case where b is 0 or c is 0, and then look at one or two different ways to solve this general form here, finishing off with the quadratic formula. So that's the plan. So first of all, let's look at the case when b is 0. In other words, there's no term involving x, and so we've just got ax squared plus c equals 0. This one's quite easy to solve. We don't actually use the quadratic formula or any other method. We just solve it like an ordinary equation. Subtract c from both sides of the equation. Ax squared equals negative c. Subtracting c from both sides. Dividing both sides of the equation by a, x squared equals minus c over a. And then finally, x is the square root of minus c over a involved. So we go through it and we end up with x equals the square root of minus c over a. And if this number, negative c over a, turns out to be positive, then we're okay, we've got a real solution. If it turns out to be negative, however, we're into the world of complex numbers, and that's something we will be looking at. But for now, we're going to stick to real solutions. Pardon me. So negative c over a is always going to end up being a positive number to give us a real solution. For example, 4x squared minus 10 equals 0. Plus 10 to both sides, 4x squared equals 10. Step 2, divide by 4, x squared equals 10 over 4, which is 5 over 2. Step 3, square roots, yeah. So calculator out, what's the square root of 5 over 2? And when we put in the calculator, we get 1.58. However, we said at the beginning that when we were talking about this last week as well, and we looked at these solutions, remember, when we have a quadratic, there's always two solutions with a quadratic equation. And if we look at this, so far, we've only got one solution. There are two solutions. And what we have to remember is that when we square root a number, the answer could be positive or negative. So in the final answer, x equals plus or minus 1.58. And the reason for that is, if I square 1.58, I'm going to get 5 over 2. If I square root negative 1.58, I'll get the same answer because yeah, that's right. Whenever you square root a number, the answer can always be positive or negative. Because once we square, it's going to end up being positive regardless of the sign before I square it. So going back the other way, we can never tell whether it was positive or negative before. So that gives us our two solutions, x equals plus or minus 1.58. So when b equals 0, it's easy to do. You just solve it as an ordinary equation. You just get x squared on its own and then square root, remembering that once you square rooted, the answer is positive or negative. Now let's look at the case when c is 0. In other words, we get ax squared plus bx equals 0. So let's look at an example of how we might cope with that. To solve situations like this where there's no c, again, there's an easy shortcut to this, because if we look at these two terms, they both involve at least one lot of x. If I had a c there as well, then I wouldn't be able to do this because there isn't an x in the c term. But because there's an x in both of these terms, I can factorize. Okay? So, factorize. Take x outside a bracket, leaving ax plus b inside the bracket. And we end up with that. X into ax plus b equals 0. Now we've got to here, now it starts to become important that this right-hand side is 0. Because what that's telling me is that the left-hand side must come to 0. So if x is 0, then 0 times anything is 0. So if x is 0, this will be true. So one solution is one solution. Because the right-hand side is 0, we can say that if x is 0, the left-hand side too is 0. Does that make sense? The other solution occurs when, can you tell me what's the other case when the right-hand, what else has got, can we make true for it to come to 0? No, not A and B. A and B are constants. We're trying to find out what we're going to put back examples for those in a second. No? When the bracket is 0. The other solution occurs when the bracket is 0, and that's the interesting one. If that bracket turned out to be 0, then it doesn't matter what value x has, the left-hand side will be 0. Okay? i.e., ax plus b equals 0. And this is a linear equation we can solve. So the first step, the right-hand side must be 0. So shift everything that's on the right-hand side over to the left, and we end up with 3x squared minus 5x equals 0. Now what do we do? Right, factorise it. So take x outside the bracket. Remember one solution, x equals 0, or 3x minus 5 equals 0. Those are my two possibilities. Either x is 0, in which case the left-hand side is 0. Am I making sense here? If x is 0, then 0 times anything is 0. Or the bracket's 0, in which case that bracket times x is always going to be 0. Anything times 0 is 0. That's why we make the right-hand side 0. So either x equals 0 or 3x minus 5 equals 0. And if we solve this, add 5 to both sides, 3x equals 5, divide both sides by 3, x equals 5 over 3. So we've got two solutions. Either x equals 5 over 3 or x equals 0. Two solutions to the quadratic equation. I can check this by putting x equal to 5 over 3 back into here, into this original equation here, and show that it comes to 0 when I put it in. If you wanted to check that it works, you would do that. So those are my two solutions to that quadratic equation. I could also show it by plotting it onto autograph and seeing where the curve cuts the x-axis. So let's try that. So to check this, I would enter an equation and I type in not 3x minus 5 squared, 3x squared minus 5x, wasn't it? 3x squared minus 5x equals, instead of putting that equals to 0, I put it equal to y. So then it plots the function y equals 3x squared minus 5x. And then you look for points where x equals 0, which are going to be where it cuts the x-axis. So you can see that one solution is at 0, as we predicted, and the other solution is at 5 over 3, about 1 2/3, which looks as though that's about right. Okay. So you can either plot it on autograph and to find the solutions, or you can do it using the quadratic, these methods that we're looking at. Okay. There are some quadratic equations that I've sort of alluded to already where there are no solutions. And you can imagine that's points where this curve doesn't cut through the x-axis. If it doesn't cut the x-axis, there aren't any solutions. So there aren't real solutions to all quadratic equations that we try and solve. So we'll come across examples of that. Finally, we have to think about what happens if we have values for a, b, and c. In other words, what about ax squared plus bx plus c equals 0. Well, there's a couple of ways I want to look at. One is one that comes in useful actually when we want to start thinking about partial fractions and stuff like that, which we'll be looking at maybe this year, probably next year, which is to solve it by factorising, and the other way is to use the general formula. So we'll look at both of those now. So let's look at an example. That's a quadratic equation. X plus 3 brackets x plus 2 equals 0. It doesn't look like a quadratic equation because quadratic equations have x squared terms in them. But if I multiply out those brackets, can you see that I'd have an x squared in there? Because when I multiply them out, I'm going to get x times x gives me x squared. So what I'd like you to do now is to multiply out those brackets, remembering that everything in this bracket has to be multiplied by everything in the bracket. So it's x times x times 2, 3 times x, 3 times 2, and then collect together like terms. So try that. Now if we look at this, and this is quite an important little step for this factorising bit, we look at the 5 and how we arrived at that 5x. We get the 5x because I've got 2 lots of x plus 3 lots of x. And that's the 3 plus the 2. So 3 plus 2 will give me the 5. And then, how have I got the 6? By multiplying the 3 by the 2. 3 times 2 gives me 6. So actually, I could have almost predicted what these numbers were going to be, because I'd say to myself, well, actually, I'm going to have x squared plus 5x, because 3 plus 2 is 5, plus 6, because 3 times 2 is 6. And we use that sort of logic when we try and go back. So, for example, going the other way, look at this example, x squared plus 7x plus 28 equals 0. So what are the missing numbers there? Think about what we did in the previous one, how I arrived at the 5 and how I arrived at the 6. What must the missing numbers be there? Deliberate mistake, not 28, 12. The missing numbers are 4 and 3, because 4 plus 3 gives 7 and 4 times 3 gives 12. So what do? We go, that means, this means that, or implies that, x plus 4 times x plus 3 gives 0. Okay? So I can work out what those missing numbers are. I factorise it. This is factorised. How does that help us solve this equation? This is the original equation here. So how does the fact that we've factorised it to get this help us to solve it? Again, it's because the right-hand side is 0. That's the key. If the right-hand side is 0, remember what we did last time, either this bracket is 0 or this bracket is 0. So again, we have two solutions. One bracket is 0 or the other bracket is 0. So again, we have two solutions. When either bracket is 0. So therefore, x plus 4 equals 0. Or x plus 3 equals 0. And that means it's dead easy to solve, because what must x be? If x plus 4 equals 0, x must be minus 4. If x plus 3 equals 0, x must be minus 3. Yeah. Solved. So we solved the equation. So again, if we go to autograph and type in x squared plus 7x plus 12 not equal to 0 but equals to y, then we'll plot the function and look for when y equals 0. In other words, the x intercept, and we get the graph. There it is, and we can see by looking at it that it cuts the graph at minus 4 and minus 3. So you can see the two solutions are negative 4, negative 3, as we predicted. So it's not always easy to factorise. Now we're going to look at a method we will look in a couple of years probably, or maybe not, called the perfect square. Maybe we'll look at it earlier than that. It's not difficult, it's just that we don't need it until that point. But that perfect square method leads to this thing called the quadratic formula, which we're going to just state now and use. Okay? In the textbook, if you look at quadratic equations, it goes through the process of the perfect square and how that's used to arrive at the quadratic formula. So if you're interested, you could look at that and see the algebraic steps to lead to this formula that I'm just going to give to you. Okay? You don't need to be able to show you can do that, but you might be interested. Here is the quadratic formula, which I'm fairly sure won't be completely new to you. You will recognize it. So this formula will work for any quadratic equation. It will work for ones where we could have solved it by factorizing. It will work for ones where b or c is 0 or a is 0. It will work for any situation. Actually, probably not when a is 0, thinking about it, because if a is 0 underneath here, if I divide by 0, all sorts of weird things happen. And so actually this formula, divide by 0, you get an infinite answer. So not when a is 0. But when b is 0 or c is 0, we could use this formula and work out the solutions. However, there's a few steps involved with this, and we've looked at some shortcuts to find the solution if b or c is 0. And it's worth certainly thinking about, can I factorize it? Which is the method we've just been looking at, this idea of factorizing it. So will it easily factorize? If it will, then you can quickly get to the solution. But there, 2 steps. We'll just go, that's the formula. Yes, it will factorize. So there are the answers. So very easy if you can see it factorizes. In engineering, often these numbers are not whole numbers, they're decimals. So you're not going to be looking for it to factorize. You're just going to put them straight into the general formula to find the solution. Or you're going to plot them in an autograph and find the solutions that way. Look for where they cut the x-axis. The use of this method is, if the curve doesn't cut the x-axis, you know there's no real roots. So as when we were looking at simultaneous equations, if you plot it and the lines don't cross, then you know there are no solutions. Equally, if you're finding the solutions to a quadratic and it doesn't cut the x-axis, then you know you're in the realms of complex numbers and there's no real solutions to this problem. So let's have a look at an example then of how you might solve using the quadratic formula. What about, to just make something up, 5x squared plus 3x minus 10 equals 10. 5x squared plus 3x equals 10. Right. Step 1, the right hand side must be 0, so if it's not, you make it 0. 5x squared plus 3x minus 10 equals 0. The next thing to do is to identify a, b and c, and this formula, the quadratic formula, works for a general quadratic that we've written down already. So it's assuming that a is the coefficient of x squared, b is the coefficient of x, and c is the constant. Yep. So therefore a equals 5, b equals 3, and c equals negative 10. Now I would write down the quadratic formula and substitute in the values. Minus b, what's b? 3. Plus or minus the square root of b squared, so 3 in a bracket squared, minus 4 times a, which is 5, times c, which is minus 10, all over 2 times a, which is 5. So at this point, I wouldn't try doing any calculating. I'd just get the numbers in and then I'd worry about the calculation afterwards. It leads to less errors this way. Okay, now before I put this into the calculator, because I recommend you use the calculator to try and do this in one hit, before we do that though, again to lead to less errors, well, because this bracket is positive, then the thing's going to become negative 3, so it's no longer necessary to put the 3 inside the bracket. The square root, The only thing to look for inside the square root symbol, it's worth just looking up for this little bit, is that I ask myself the question, is this bit in here going to be negative or positive? I've got a minus times a minus is going to give me a positive. So I know I'm going to end up with this bit squared plus this bit, 4 times 5 times 10. That's the only thing I'm really interested in, and I can work it out for this case. It's not that difficult. But if these were not whole numbers, they were decimals, I'd put the whole thing in the calculator, but I would end up putting a plus in the middle. So it's going to be 9 plus 200, because 4 5s are 20, times 10 is 200, all over 10. So for this example, I'd go as far as I could before I start putting it into the calculator. Now, I'm going to key this into the calculator. What do I do about this, though, the plus minus? Yeah. You do the plus first, and then leave the calculator in the calculator and scroll back and change the plus to a minus. And then, rather than redo the whole thing twice on the calculator, just change this from a plus to a minus. So try it and see what you end up with for the solutions. So x equals 1.15 or negative 1.57, rounding to 3 significant figures. So to quickly recap, we were going to look at methods to solve quadratic equations which assume that the right-hand side is 0. Here it is. We have 3 cases. One where b is 0. That's easy to solve. You just solve the equation. Get x on its own, hoping that when you get to the square root at the end, it's a positive square root. If it's negative, at this point you're going to have to stop and say it's a complex solution. But if it's a positive solution, you can find, because if you try and find the square root of a negative number, you'll end up with an error on the calculator. So that's the first case. Second case is when there's no constant, and to do that you just factorize the thing. And if there's no constant, no c, one solution is always where x equals 0. And then you just solve the bracket to find out what the other solution is. For example, there. And there's the thing plotted in autograph. One solution is always at 0 when c is 0. And that's because actually, just like any equation, c, like the equation of the line, is the point at which it cuts the y-axis. So when c is 0, it always cuts at 0. So whenever c is 0, it will always cut through at 0. So one solution is always 0. What about the general case then? Quickly look and see if it factorizes, and there's a few examples in the textbook that get you to practice that, and so you know they're going to factorize, so you can try those and try and see this method work. Because if it factorizes to end up looking like this, then it's very easy to say what the solutions are. X equals negative 4 to make this bracket, or negative 3 to make that bracket 0. So very easy if you see those shortcuts. If you run out of shortcuts, then you have to rely on the quadratic formula, which is this. Okay, so it's worth trying to remember what that is. Remembering a represents the coefficient of x squared, b is the coefficient of x, and c is the constant. So you just plug them in. One last thing that's worth pointing out, this, the root, for the same reasons as we've discussed already, it must be positive for a real solutions. In other words, again, if that square root turns out to be negative, there's no real solution. So a lot of people, engineers, will often work out what the root part of this quadratic formula is quickly in their heads, a rough idea, to check whether they're not going to get a real answer or not. Okay. Let's look back at this last week. Remember we had these two simultaneous equations, and we got as far as here. We solved these simultaneous equations by substitution. So let's remind ourselves of this process. Here are the two equations. We used substitution to do it. We rearranged equation 2, that's this one, for y. So if you rearrange equation 2 for y, we get y equals 10 minus 8x over 10. Which we substituted into 1. So instead of y in this formula, we're going to write 10 minus 8x over 10, which we did here. And then we play around with it. 3x squared minus 4 times 10 minus 8x over 10 equals 2, this line. Simplified it, and we end up with this. That's a quadratic equation. So now let's try and finish this off. What's the first step? Get rid of the 20 by minus 20 from both sides. So I'm going to get 30x squared minus 60 plus 32x equals 0. Or 30x squared plus 32x minus 60 equals 0. Can't take an x outside a bracket here, Alex, because there's this constant here. However, there is one little thing I can do to help myself. Anybody suggest it? So we can, now we've got this to solve, we can either put this in as it stands in the quadratic formula, where a is 30, b is 32, c is minus 60. We can try and make it smaller by dividing through by 2, or suggestion is made to divide through by 10. 3x squared plus 3.2x minus 6 equals 0. Good idea, okay? Because the calculator, if you're going to use a calculator anyway, it doesn't matter whether it's a whole number or not. We could go the whole hog and divide by 3 to get rid of the 3 there as well, okay? So this, in other words, you can try and make the problem easier, but at the end of the day, you've then got to now finally put these numbers into the quadratic formula and get the values for x. So would you like to carry on and finish that off? Find the values for x for me, please. So it looks like we have solutions of 0.98 or minus 2.04, and if we put it into autograph, that seems to confirm it. Let's go back to the original problem now. We've got x, so now we can substitute that value for x back in, or those values for x rather, back into this formula to find y, okay? Remember, the original problem was to find the two values for x and y, solving by substitution. So now we can put these values of x back in to find y, and show that the two solutions which we looked at on autograph are there and there. So we've got the x values now. Look, x is about minus 2.04, and x is about 0.98. We've now got to just find out what these y values are here, and then we solved it, okay? So have a look at chapter 11 in the textbook now. Having gone through this and just confirm, look, if we go back to this, we've now got the values for x, so you can confirm, go back to the original equations that we had in these simultaneous equations to find y, and confirm the values on the graph. But what I want you to do now is to look at the chapter. I've not gone through all the possibilities, so there are other little examples you could look at, and they're in the textbook, and try some questions in this exercise. Once you've had a look at those, you'll see the perfect square method highlighted. If you're interested in looking at the perfect square method, have a look at that. But I want you to get on to solving quadratic equations by the formula, using the formula. So look at that section, 11.4, and then the exercise that follows on from the end of that. And then 11.5, some practical problems. So that's the sort of things that I need you to be moving towards, okay? So Tommy, you can look at some of these practical problem questions. Okay.